This section explains why the opening chapter builds two languages side by side so that later chapters can prove they are one. On the geometric side, a site is a small category together with a Grothendieck topology, where covering has been abstracted away from families of open subsets and into sieves. A site presents a topos of sheaves. On the logical side, a geometric theory presents its syntactic category. The objects there are formulae in context, and the covers come from provable disjunctions. The thesis of the chapter is that presentation is the operative notion. A topos always arrives as a presentation, and by many inequivalent sites at that. A theory is one such presentation, and the soundness and completeness results of section 1.4 certify that nothing is lost in the passage. Everything downstream lives inside that many-to-one map, from presentations to the topos they present. The bridge of Chapter 2 is its immediate exploitation. This section explains what a classifying topos is and how the bridge technique turns one into a transfer machine between unrelated theories. A geometric theory determines a topos that represents its models in every Grothendieck topos. That topos is what survives change of presentation, so it carries the theory's invariant content, its Morita class, two theories with nothing in common that share one classifying topos become two sites for the same object. The bridge works like this. Pick a topos theoretic invariant, then read it down each presentation through a site characterization. The two readings must agree, and that forced agreement is a transfer theorem between theories that never mention each other. Caramelo's arches are those site characterizations. The deck is the Morita equivalence. Nothing in the machine is specific to logic. It is the standard move of computing one invariant in two charts, made industrial. The rest of the book is instantiation. This part explains why adding axioms to a theory and adding covers to a site are the same act. Take a geometric theory. T, extending it by new axioms does exactly what refining the Grothendieck topology on its syntactic site does. Theorem 3.2.5 makes that identity exactly one such quotient of T taken modulo syntactic equivalence stand in bijection with subtoposes of the classifying topos. Set bracket T. Set bracket T. Each quotient is classified by the topos of sheaves on the syntactic category. CT with respect to a topology. J. The consequence for logic is that provability turns into a closure operator. A deduction relation is a Grothendieck topology, in the strict sense, not by analogy. The chapter's role in the arc is to make the bridge technique act on theory extensions rather than on single theories. Once the bijection is in hand, whatever structure the lattice of subtoposes carries descends onto the lattice of axiomatizations. A deduction theorem for geometric logic then drops out of the proof. Theoretic reading of that same bijection. This section explains what happens when a theory stops being a point and becomes an element of a lattice. The duality from Chapter 3 runs between three things: quotients of a geometric theory, Grothendieck topologies on its syntactic category, and subtoposes of its classifying topos. That duality reverses order. So, the co-hiding algebra of subtoposes arrives on the theory side as a complete hiding algebra. Its operations read off directly. Meet is the sequence provable in both theories. Join is the union of the axioms. The implication is the one operation geometric logic gives you no reason to expect. The chapter is a single move repeated. Take an operation on subtoposes, Booleanization, demorganization, open, closed, atoms. Read it back across the duality. Collect a construction on theories. Transport of structure with logic on the receiving end. This section explains how a change of topos acts on models and why the machinery leading up to it exists. A model is a functor, so changing topos is composing functors. That is the whole chapter. Diaconescu makes the T models in E, the flat continuous functors on the syntactic site. A geometric morphism then acts on models by composition, and the work here is computing that action explicitly. Theorem 5.2.5 delivers it. The extension of a flat functor on a small category, K of set-based models, sends the formula object bracket x vector, phi, to the colimit of F composed with the projection from the category of elements of that formula object. Everything preceding exists because those colimits are taken in an arbitrary Grothendieck topos, where set-based filteredness arguments do not survive, indexed colimits, E-filteredness, E-final functors, the indexed Yoneda representation. Chapter 6 converts the statement that the extension is an equivalence, naturally in E, into pre-sheaf type. This section explains what makes a theory of pre-sheaf type and how that condition gets moved from the classifying topos down into models. Pre-sheaf type is a property of the classifying topos, and the chapter's move is to make it visible entirely downstairs in models. Theorem 6.3 presentable. 1 says that a theory, T is classified by the functor category from K to set exactly when every T model in every Grothendieck topos, E is canonically in every Grothendieck topos, E is canonically an E-filtered colimit of constant models coming from K, and each such constant model is E-finitely presentable. The familiar set-level fact that models are filtered colimits of finitely presentable ones becomes a criterion once it is required uniformly, internally, across all toposes at once. That uniformity carries the whole content. A single topos version is far too weak. The chapter is the admission gate to the class, where the bridge technique of Chapter 2 runs cheapest, pre-sheaf toposes, carrying their own canonical site. This section explains how adding vocabulary to a theory is the same act as mapping into its classifying topos. Expansions, meaning new sorts, symbols, and axioms laid over an old signature, induce geometric morphisms from the classifying topos of the new theory to the classifying topos of the old one. The correspondence runs onto every morphism into a classifying topos is somebody's expansion. That is Theorem 7.1.5. 2 syntactic restrictions, then name 2 topos, theoretic classes. Adding no new sorts gives localic. Adding no new definable content over the old sorts gives hyperconnected. The hyperconnected localic factorization therefore becomes a construction in logic. Christen each old formula with a fresh relation symbol, and that intermediate theory is the factor. The chapter's role in the arc, structural surgery on toposes, performed as vocabulary surgery on theories. This section explains how adding axioms to a theory of pre-sheaf type is the same move as choosing a Grothendieck topology. Take a theory, T, of pre-sheaf type. It is classified by the pre-sheaf topos on C, the category of set-valued functors on C. Its quotients, the theories you get by adding axioms, correspond to topologies J on C op by the duality established in Chapter 3. Theorem 8.1.3 pushes that correspondence from syntax into semantics. The models of the quotient are exactly the J-homogeneous T models, those in which every generalized element defined on a finitely presentable piece extends along some arrow of each J. Axiom becomes covering. Covering becomes lifting property. The anchor is dense, linear orders without endpoints in section 8.1.1.1. These are precisely the homogeneous linear orders for the atomic topology. Density is extension along the inclusion of 2 into 3 into finite ordinals. Given 2 points, a third slots between them. Quotienting a theory becomes a computation on a site. This part tests the criteria against real theories. A criterion is worth what it can decide, and Chapter 9 is the test bench where the general criteria of Chapters 6 through 8 get fired at concrete cases. One pattern carries most of it. When a theory's finitely presentable models are exactly its finite ones, the classifying topos is pre-sheaves on that category of finite models, and the work collapses into localization arguments. Mordyke's abstract circles and Johnstone's Dyer's fields get fully constructive proofs. With the circles case repairing an argument, Caramello notes appears incomplete. Algebraic extensions of a field, locally finite groups, and vector spaces with independent predicates arrive new. The chapter's sharpest move is negative. The injectivization of groups fails and receives a pre-sheaf completion instead. A decision procedure must also decide against. This chapter proves a point instead of stating one. The bridge technique from Chapter 2 is a generator, and the way to demonstrate a generator's reach is to crank it in directions that share nothing with each other. Watch the list. Restriction of Morita equivalences, Lovade's boundary problem on subtoposes, Fra-Isse's theorem, topological Galois theory, the maximal spectrum of a commutative ring, compactness, fragments of geometric logic. No shared subject matter, one shared move. Each result comes from choosing a topos, invariant, and reading it across 2 presentations of the same classifos invariant, and reading it across 2 presentation topos. The structural claim underneath, a classifying topos, is where theories that cannot be translated into each other nonetheless meet and transfer.